Hello everyone, this is Kevin from MBT. In this session we're going to simulate the battery post-discharge using the ECM model under MSMD battery model in Ansys software. As you may already know, the battery post-discharge is a high rate discharge of a battery. Actually, the higher the C rating, the more power the battery can give out. One of the most important applications of this simulation would be in hybrid pulse power characterization or HPPC test of a battery. As you can see on the right side, we have the HPPC test flowchart for a battery. At first, the battery is fully charged, then it is discharged by using a 1C current for 6 minutes. After that, the battery is preserved for an hour, and we will continue this cycle for 10 times or more to finalize the HPPC test, and that would be when the battery is fully discharged. In industrial level, a good example of battery pulse discharge would be in pulse lithium polymer batteries, which use high discharge rates as 35, 45 or 65 C rates. In this session, we're going to have two simulations of the battery pulse discharge. In the first one, we change the battery operating conditions, and that would be the C rate of the battery. So we alternate the C rate between 0 and 3, and we run each calculation for 5 minutes. The time step size would be 30 seconds, and the number of time steps for each calculation would be 10. As you may already noticed, alternating the value of C rate between 0 and 3, it would be a little time consuming and boring. So in the second simulation, we introduce a time schedule profile option. With this time schedule profile option, we don't need to manually change the value of C rate for each calculation. So let's go through the software and start the simulation. So now here we are in the Ansys software. As you know, the geometry and the mesh are already created. If you want to know how to create the geometry or generate the mesh, you can go on videos on the elementary level of lithium-ion battery simulation, and the links for those videos are given in the description. So now we go to the Fluent Solver. We use double precision and serial for processing. So the mesh is loaded. As the battery pulse discharge is a transient simulation, we should choose the transient for the time. On the physics tabs, we enable the energy equation, and in the solution tab, we deselect the flow equation as there is no fluid flow in the battery cell. Before starting the simulation and defining the MSMD battery model, we perform the mesh check. As you can see, the minimum volume is positive, so everything is okay. And now we define the MSMD battery model. So we simply type define models add-on module, and we select 8 for the MSMD battery model. As you can see in the models, we have now the MSMD battery model. We enable the model, and you can see the tabs. So for the eChemistry model, we're going to use the equivalent circuit model or ECM model. The nominal cell capacity would be 14.6 amp hour, and the C rate for the first calculation would be 3. By continuing the cycles, we're going to alternate the value of C rate between 3 and 0. So for the first simulation, which is a discharge simulation, we use the C rate as 3. One point here that you should keep in mind is the minimum stop voltage, which is 3 volts. As time goes by, after each calculation, by C rate of 3, the value of positive potential of the battery cell will decrease, and this is a UDS condition to stop the simulation when the potential is reached to the value of 3. So now we go to model parameters. We should choose 0.85 for reference capacity, and initial state of charge would be 1. The conductive zones, we have only 2 zones, active component and tap component. We don't have bus bar in a single cell battery. So for the active component, we select the cell zone, and for the tap components, we select negative zone and positive zone. In the electric contacts tab, we should just simply select the negative tab for the negative tab and the positive tab for the positive tab. So now we're ready to print the battery system connection information and see that the battery connection info is done. Okay, now we're ready to continue and introduce the materials. For the materials, we should define 2 materials. The first one would be for the active component, which is the cell zone. So we give it a name as active material. The formula would be A_M. We should edit the density to 2092. For the UDS diffusivity, we use the option of defined per UDS. So we have 2 UDS values, UDS 0 and UDS 1. For UDS 0, we define a value of 1.19 e to the power of 6, and for UDS 1, we select a value of 9.83 e to the power of 5. So it asks us to change or create mixture and overwrite aluminum, and we say yes. Other parameters are remained the same. So as you can see, now we have the active material. The name is correct, density is correct, and the UDS diffusivity is defined per UDS. Now we should bring another material for the electrodes. We use the solid type to bring the copper, and we copy the information. So now you can see we have the copper in the solid materials. We edit the name to tab material, and we give it a formula. We remain the density as the copper density, but for the UDS diffusivity, we select the user-defined function and use the default user-defined function of Ansys which is the battery E-count MSMD bats. So we overwrite it again. For the electrical conductivity, we use a different value of 1e to the power of 7. So we change on create and close. So now we have the tab material ready. The name is okay. Density is the density of the copper. The UDS diffusivity is selected as a user-defined function, and the electrical conductivity is not edited, but we make it again. So now we can check, okay, everything is okay. So now we can go to the cell zones and assign each material to the specific zone. So for the cell zone, it should be the active material, which is okay. We have 2 materials. For the negative zone, we should use the tab material. And for the P zone, we should use again the tab material. Now we go to the boundary conditions. As you can see, we have many surfaces and many zones, but we only need to define a heat transfer value for the heat transfer convection. So we select the cell zone, and as we already enabled the energy equation, we can define different thermal conditions. So for the convection, we use a value of 5 for the heat transfer coefficient. The free stream temperature would remain as 300 Kelvin. So now we're okay. And we want to copy the same boundary condition as we discussed for the other zones. So we use the copy option. We copy the boundary condition from the cell zone to the negative zone and the positive zone. So if we check one of these, we should see that the heat transfer coefficient of 5 for convection should be selected. Okay. We skip the methods and controls for the simulation, but we want to define a report plot. So in the monitors, we define a new report plot. We want to capture the potential of the electrode over time to see how the potential decrease by the simulation of the pulse discharge. So we're going to give it a name as UDS surf V plus, and we're going to use the x-axis label for flow time, and we use a surface report of the area weighted average for the positive zone So we report the plot and use a user define a scalar for the potential phi plus. So now we click OK. Okay. So now we have the report plot here. Which the x-axis label would be the flow time and the y-axis label would be the area weighted average potential phi plus for the electrode. So click OK. Now we can initialize the solution. We use the hybrid initialization. So the initialization is done. We go to run the calculation. Number of time steps would be 10 and the time step size would be 30 seconds for each calculation that we said it must be 5 minutes. And for the maximum iterations per time step we use 10. So everything is ready. We can start the first calculation. We simply used the 10 value for the maximum iteration per time step because we don't need to get a very accurate result. We just need to see the behavior of the battery cell to the battery pulse discharge. So the value of 10 is enough to analyze this behavior. And as you can see, after one time step, the plot for the area weighted average of potential is ready to show what's going on. As this is obvious, the value of potential is decreasing by the C rate that we are defined as 3. I just stop the video recording and get back to you after the calculation is done. So the first calculation is complete. As you can see, the value of potential is decreased. And now we want to change the value of C rate from 3 to 0 and have the calculation again for 5 minutes. So we go to run calculation and continue the simulation. Now the battery is preserved for 5 minutes with a C rate of 0. So the potential value must increase to a value higher than the previous point. So now the second calculation is complete. As you can see, the value of potential has been increased. And now we should alternate the value of C rate again back to 3. run the calculation again. We should keep doing this cycle and see after how many cycles and how much time we reach the final point, which is the minimum stop voltage of the battery cell that we already defined as 3 volts. So as you can see, the calculation is finished, and if we look at the plot for potential, we can see that after 7 calculations, that each calculation has lasted for 5 minutes, we have reached the minimum stop voltage of the battery cell, which was 3 volts. So if you can see here, the time flow is around 2100 seconds. So in the second simulation that we're going to introduce a time scheduled profile for the C rate, we need to continue the calculation until this time flow, which is roughly about 70 time steps. That would be for each time step 30 seconds. So let's go and see how we can define this time schedule profile for the C rate. So the time schedule profile is defined in 3 columns. It could be defined in a text file, and the first column defines the time, the second column is defined the electric load value, and the third one defines the electric load type. For the electric load types, we define each load type with an integer. The 0 defines the C rate, 1 defines the current, 2 defines the voltage, 3 defines the power, and finally the 4 defines the external electric resistance of the battery. So as you can see on the right side, we have defined all these numbers. The third column would be all 0 because it defines the C rate, and in the first column we define the time. As you understood from the previous simulation, the time step size is 30 seconds and the number of time steps for each calculation is 10, so the overall time for each calculation would be 300 seconds. So as you can see in the numbers in the first column, from 0 to 300 seconds we have a C rate of 3, and from 300 to 600 we have the C rate of 0, and we continue this until 2100 seconds of flow time. This time it was defined by the previous simulation. So let's go to the Ansys software and see what happens if we define the C rate alternation with this time scheduled profile. So now in order to import the time scheduled profile, we need to go to the MSMD battery model, and under electrical parameters, and from the solution options, which you choose using profile. The profile type is time scheduled, and we browse the text file for the C rate alternation, and we click OK. So now once again we should initialize the solution, and before running the calculation we need to edit the number of time steps to 70 in order to cover the whole flow time of the simulation. And now we run the calculation. So the whole calculation starts again, and the potential plot will start after the first time step. So we let the simulation to go on, and at the end we'll check if we get the same result as in the last simulation. So the simulation is finished. If we check the results of the potential, we can see we have the same result for the pulse discharge with the flow time of the same value of 2100 seconds. So this is all for the battery pulse discharge simulation in Ansys software. If you have any questions, please leave those in the comments and I will get back to you as soon as possible. Thank you all.